Hello and welcome to another video. In this video we're going to be working on find the town judge. And in the problem there are n people labeled 1 to n, and there's a rumor that one of these people is a judge. If a judge exists, then the judge doesn't trust anyone and everybody else trusts the judge. There's exactly one person that satisfies these conditions. You're given an array trust where trust I, A, B means that person A trusts person B. If the trust relationship does not exist in the trust array, then such a trust relationship does not exist. Return the label of the judge if there is a judge, or -1. So if we take a look here, when n equals 2, if 1 trusts 2, that means everyone trusts 2, right? Except for 2, because the judge doesn't have to trust themselves, and 2 doesn't trust anyone, so 2 would be the judge. In this example, 1 trusts 3 and 2 trusts 3, and 3 doesn't trust anyone, so 3 is the judge. And in this example, 1 trusts 3, 2 trusts 3, and 3 trusts 1. So there is no person who everyone except for that person trusts, and that person doesn't trust anyone, right? You don't have these conditions met, so you just return -1. So this problem is basically just can you build a graph? Or can you just have a couple things? And all you need is a couple things. Is you need 2 data structures, or you can combine into one. So that says for every number 1 through n, write down or calculate how many people that number trusts, right? That's 1. And the second one is for every number 1 to n, calculate how many people trust that person. And so we can basically just have a data structure for both of these. And then when we take in these edges, we can just put this in here. So let's say that for the person that, or the number, the people that person trusts, we'll make a label for that. So we'll call that trust, or I guess we'll call that I trust or something. Not the best name, but it'll work. And then the second one is how many people trust that person. So we can call this trusts me maybe, or trust me or something. And so basically what would happen is we can just go through this example and show what would happen. So remember, in all of these edges, A trusts B. So if 1 trusts 3, then for 3, there's one person that trusts that person, right? Number 1. And then I trust 1 trusts 3. So 1 has one person they trust. And then you can basically just have this counter of each of these things. So 1 trusts one person, and now 3 has one person that trusts them. So yeah. And then let's go through the next example. So 2 trusts 3. That means there's one more person who trusts 3. So 3 goes to 2. And 2 trusts 3. So 2 trusts one person now. And finally for 3 trusts 1. So 3 trusts one person. And 1 has one more person that trusts that person. So 1 has 1. So at the end, 1 trusts one person, 2 trusts one person, and 3 trusts one person. And there's 2 people that trust 3 and 1 person that trusts 1. Then basically all you have to do is just go through your numbers, and you're looking for a person who n-1 people trust, right? Every single person other than that person has to trust them. So if n equals 3, 2 people have to trust that person. So you're looking for someone who 2 people trust, and that person also has to not trust anyone. And there's nothing like that in the list, right? Because there is a person who 2 people trust right here, number 3. But 3 trusts 1, so there is no result here. And so that's the idea. You basically just make these 2 lists of people I trust and people who trust me. And then you look for a person who n-1 people trust, right? So for this person, the people who trust that person should be n-1, and that person should not trust anyone. And if you do find that one, then you will return it. Otherwise, you will return -1. And there is a little thing that there's this third condition. But this is kind of implied. So if you think about it, there can't be more than 1 judge, because in order for the person to be a judge, if there's n people, n-1 people have to trust that judge, right? And that judge can't trust anyone. So if there's 2 judges, in order for there to be a judge, n-1 people have to trust that judge. Well, if two judges don't trust anyone, then you can't have n-1 people trusting that judge, right? If there's 2 judges, then n-2 people is the most people you can have trusting everyone, because 2 people will trust no one. So this is already implied. So if there is a person who satisfies these 2 things, then that's your answer. You don't have to check if there's like a duplicate or anything. But that's basically it. So we can just make 2 dictionaries of the number of people who trust that person and the number of people that person trusts, then just go through the values. Now, another shortcut you can do is, let's say n is like 1,000, but there's only 3 edges. Instead of going through numbers 1 through n, we can just go through numbers in trust me, right? So because for n is greater than 1, there has to be people that trust that person, right? In order to be a judge, if n is greater than 1, so let's say n is like 5, that means that judge will exist in this dictionary, right? There will have to be 4 people that exist that trust this person. So instead of going through numbers 1 through n, we can just go through all of the keys in trust me, and then we can just check, is their value what it needs to be, and are they also not in this I trust dictionary? Now there's one little caveat here. So let's say n equals 1. I think they might have, no, they don't, but there is an edge case here. So if n equals 1, and like a person can't trust themselves. So if n equals 1, that person's automatically the judge, because you need 0 people to trust them, and they can trust 0 people. So yeah, if n equals 1, it's basically going to be automatically the judge, because I think they tell you, I think that's one of the constraints where like a person can't be in here twice, as far as I remember. And so that would be the caveat there. So if n equals 1, then you can just say that 1 is always the judge, because the person can't trust themselves. And otherwise, yeah, you will just go through all the people in here, and that would save you a lot of time, right? Because if you have 1,000 people, but you only have a few edges, there's no point. Like if you have 1,000 people, but people only trust 1 or 2 people, you can just look through 1 or 2 people instead of 1,000. So that'll speed it up practically. So we can code that now. So we can say I trust is going to be the dictionary of people I trust, or that person trusts. Like I said, probably can come up with a better name there. And trust me is going to be people who trust that person. So default dict spelled there. Okay. And now we just have to go through all of our edges. So we can just say like for x, y, and trust. We can say it's going to be x who trusts y. So I trust of x is going to increase by 1, right? Because I trust is like, we can even comment this to make it more clear. This is people who I trust, or number of people who I trust. And number of people who trust me. So x is trusting y. So x trusts 1 more person. And the number of people who trust y increases by 1 as well. So trusts me of y increases as well. And then all we have to do is, like I said, all we have to do is look through the keys in trust me, because as long as n is greater than 1, that will always be the case. So we can say, like, in order for there to be a judge, if n is greater than 1, and that judge has to be in this dictionary. Everyone has to trust that judge. So we can say for key in trusts me, and then we can just check for those 2 conditions. So we can say if if key not in I trust, right? Like that person should trust no one. So if key not in I trust, and trusts me key. So this has to equal n minus 1, right? So if there's 3 people, then 2 people have to trust that judge. So this has to be n minus 1. Then we can just return that key. And remember, there can't be multiple judges, because you would never be able to satisfy those conditions. Otherwise, you can just return -1. Or there's, like I said, there's one more edge case here. So if n is 1, so we can say if return -1 if n doesn't equal 1, else 1. Because if there's only 1 person, then a person can't trust themselves. So that person would automatically be the judge, because n minus 1 people would trust that person, right? 0. And that person would trust 0 people, and they'd automatically be the judge. So we can, let's see here. Trust me, probably misspelled it. Yeah. All right. And there we go. And as far as the runtime, it's kind of all over the place. But in theory, this should be a little bit faster than going through all of your going through 1 through 1,000. So let's actually take a look at this really quick. Yeah, so I did miss this. So yeah, all the pairs are unique, and the person can't trust themselves. So that's why this section works here. So yeah, if n equals 1, if a person can't trust themselves, then basically your trust edges will always be empty. And then this person will always be the judge because 0 people will trust him and he will trust 0 people, which will satisfy both of these, right? So n-1 people trust him and he trusts no one. So that's why this is the case. And we can even show this actually. If we just return -1 as a default and we run this, we're going to hit this edge case. And there we go. So that's why you need it. And then yeah, so this is going to be all for this one. So let's actually do the runtime and everything. So basically we are looping through all of our edges. So let's just say this length trust is just n. So we're looping through this one time, and then we are looping through it again. Yeah, we're looping through. It's going to be worst case O of n here. It could be less in practice. Like if all these edges are completely unique, like if there's 1 to 2, 1 to 2, 3 to 4, and so on. If there are if some keys here have a value greater than 1, this will be less than O of n for the second loop, but it'll be worst case O of n. But either way, it's O of n for length of trust, not this n here. So we can even say that. So we can say O of length of trust. Because, like I said, if there's 1,000 people, we're only checking the people who people trust. We're not going through 1 through 1,000. So in practice, this will actually, I don't know why it's curious it's so slow, but anyway, in practice, this will save us a lot, depending on the actual test cases. I guess all the solutions here are roughly the same, so it's not too much of a big deal. But yeah, because if there's 3 edges and 1,000, if n's 1,000, this will be really fast. So yeah, and space. So this will be worst case O of n as well, right? Because every different person has. So I think this is not O of n. This is this is this n here. So this is O of n where the n input, and this is the length of trust. Because actually, no, I think this can also be worst case O of length of trust, because we're only storing actual people who we're only storing things when there's an edge. So I think this is also length of trust actually, because if there's 1,000 people but there's only 2 edges, our dictionaries will only have 2 keys in them regardless, right? So this is also worst case length of trust, not this n. But yeah, I think that's going to be all for this one. So hopefully this is helpful. And this is just a basic, can you build a graph? Normally, when you would build a graph, what you would do instead of doing it in this format, you would have your node as your key. And then instead of having 2 dictionaries, instead of that, you would have a list here as your edges. And then every time you have a connection, you would put another node in here. So for every node, you'll have a list of nodes connected to. But in this problem, it's simpler than that, so that's not necessary. So we can just have a number of things it's connected to. We don't really need to care what exactly it's connected to, just to count. But yeah, it's going to be all for this one. Hopefully it was helpful. And if you have any questions, as always, write in the comments. And thanks for watching.